All right, I'm back. And all I'm going to do in this presentation is show how the different microstructures form as you're cooling a two-phase material. And so I've got this same copper-silver phase diagram up. If we look at that 5 weight percent silver alloy and talk about what happens at the microstructural level when it is above the liquidus, then all I have present is liquid. Once I cross the liquidus, and this is hit the liquidus right there. Once I cross the liquidus, I'm in the region that is alpha plus liquid. And so alpha, the solid, starts to form in that liquid. So this image of the alpha beginning to form in the liquid, and then as I get toward this solidus, right there, approaching all solid, I have the alpha grains getting larger and consuming all the liquid, so that once I get into the single phase region, I have all alpha. And these lines that I see, these are the grain boundaries. So you can think of each of these different areas, I guess, in 2D as an individual crystal. Each of them, the atoms are oriented at a different angle with respect to the surface. So this is what's happening when I'm in the single phase region, the alpha region. There's no real change from above 1000 C to just above 700 C. And then when I cross into the two-phase region, into the region that is alpha plus beta, which means this line is a solvus line. Once I cross there, I still have these alpha grains, but now my beta will form at the alpha grain boundaries. Now, it's important to remember, none of this is liquid in the liquid form. All of this is happening in the solid form. Remember, beta is on the far right side of the phase diagram. It's rich in silver, whereas alpha is poor in silver and rich in copper. So what's happening here, as I'm cooling, is that the amount of silver that I can get in to the alpha is dropping. It's approaching zero. And so what has to happen is that there has to be a second phase that's formed that can take a high amount of alpha. And that's what's happening here with the beta forming. It forms at the grain boundaries because that's the lowest energy place for it to form. There's all kinds of activity or energy at the grain boundaries, and so any change is going to first be most likely to happen at the grain boundaries. All right, so that's for our 5 weight percent silver alloy. On the opposite side of the phase diagram, where I have liquid, and then I have an area where beta is forming in the liquid, and then I have an area where it's all beta, and then I have an area where it's all alpha plus beta. It's just exactly like what I had at 5%. So I have all liquid when I'm above this liquidus line. Once I cross that line, then beta starts to form in the liquid until I get to the solidus line here, and I'll have all beta. So once I cross this solidus line, I should have all beta like this with just grain boundaries. And it'll be just like that from throughout the beta region. So nothing really changes. I just have beta as I go from this solidus line to this solidus line. Once I cross the solidus line, now I'm in the region that has alpha plus beta. And I'm mostly beta, and I get to a place where beta is going to, is taking on more silver, but it can't take as much copper. And so alpha forms at the beta grain boundaries, like that. So the 5% that we just saw, and this 95 or 97 or whatever, they are on two sides of the line that defines the eutectic temperature. So this line, which was at 770 or so C, that's a eutectic line. And we just looked at alloys that are either over here or they're over here. They're to the right of 91.2 in composition, and they're to the left of 8 on this side. And so they're called off eutectic. Alloys. And that'll be more meaningful when we look at what happens with eutectic alloys. So that's what's next here. Now we're going to look at the eutectic composition, which was 71.9 weight percent silver, cooling from all liquid into the two-phase region. So notice I'm not going through a region where beta forms in the liquid. I'm not going through a region where alpha forms in the liquid. And so all the way down to the eutectic temperature, I only have liquid. But once I cross that line, I go from all liquid to alpha and beta. And the alpha and the beta form this kind of microstructure. Layers of the two solid phases. And they're alternating. And how they form, fortunately I can't figure out how do I go about getting more than one color. But if I have my, fluid liquid state and I'm cooling and I cross the eutectic temperature, then liquid is no longer stable. and the system is trying to make something happen. And so what will happen is I'll start to form a layer of one of the two phases, and it'll move into, it'll grow in away from where it forms or where it nucleates toward, or away, just away from where it nucleates. So this might be alpha that formed, and alpha has a lot of copper, doesn't have a lot of silver, and so it pulls the copper away from the nearby areas, and that creates a layer that's of beta that has more silver and less copper. And this continues, this alternating layer continues, and this grows in, and it's happening at other places at the same time. Until I get the whole area is filled with these alternating layers. So I had liquid, and now I have this all eutectic microstructure. That's what this is. And that only forms 100% if my composition is at the eutectic composition. And that won't always be the case. In some cases, it will be less than the eutectic composition. In some cases, it'll be more. So first we'll look at less than the eutectic composition. So remembering that our eutectic composition was 71.9, I believe. And so here we have a composition that's between the two. It's 20. It's between the 8 and 71.9. And we call this, because it's less than the eutectic composition, we call it a hypo, meaning less than, a hypoeutectic alloy. Okay? And so what happens to that alloy as we cool? Well, if I'm above this liquidus line, it's all liquid. But as I cross that liquidus line, I start to form, so this is my liquid, I start to form alpha in the liquid. Just like what happened with the 5 weight percent as we crossed that line. And as we cool, as we go from the liquidus line to this eutectic line, there will be more and more alpha forming. But it won't fill the whole field. We won't get to 100% of it when we get to the eutectic temperature. So I've got my liquid, and I've got this alpha that's starting to form. And this alpha is unique. It's alpha that forms above the eutectic temperature. So it's called pro-eutectic alpha. That's this alpha, pro-eutectic alpha. Alpha that formed above the eutectic temperature. So when I am ready to cross, when it just above this eutectic temperature, I'm going to have some liquid and some alpha. The alpha won't do anything. It'll remain. And that would be these bigger areas here. And all that was liquid will form this layered microstructure. So wherever there was liquid, there's now eutectic. Just layers of alpha and beta. So this here, that's my pro-eutectic alpha. And wherever I see these layers of alpha and beta, this is my eutectic. So when the transformation crossing the eutectic is finished, I have basically two different microstructures kind of mixed up together. One of those microstructures are these larger grains of alpha, and the other microstructure is this layered structure. And they offer two different kinds of properties. And so what my properties are going to be for this alloy are very much a function of the distribution of the alpha and the beta. Okay? So now we're going to look at, well, this is what you have for your homework. These two different compositions. And so you'll see in the homework assignment that I've got this image with points 1, 2, 3, 4, and 5. And I ask for you to sketch what would be present at each of those temperature composition combination. Okay. So we just looked at an alloy where I had less than the eutectic composition, less than 71.9 weight percent alpha, or sorry, weight percent silver. I had less than that, and we call that a hypoeutectic alloy. Now I've got an alloy that has between the eutectic and the far right end of the eutectic line. And so this is a hypereutectic alloy. And it's going to be very analogous to what we looked at a moment ago. So as it crosses into the two-phase region from all liquid into the liquid plus beta, as the beta starts to form, that's what we see here. So this is liquid, and this is beta. Beta is forming in the liquid, and as it get to just above the eutectic temperature, I'll have these large grains, well, relatively large grains of beta in the liquid. When I cross that line, that temperature, any liquid that's present will undergo the eutectic reaction and form layers of alpha and beta, like that. So here are the large grains of beta that formed above the eutectic temperature. So this is pro-eutectic beta, formed above the eutectic temperature. And then I've got these areas of alternating layers of alpha and beta. Okay, and so again, there's our the images for what I want you to draw sketches for each of these 5 temperature composition combinations based on what we've learned. And I think that is the end here. I just have a blank